So welcome back. Hope you had a good 3-day weekend. I hope you also remember the basic definition of a logarithm because this week we're now going to start talking about log functions, and remembering the definition of a logarithm will definitely come in handy. We've broken up this week's lesson into two screencasts to try to keep them a little shorter. So in this first one, we are just going to talk about how to graph basic log functions, that is, functions without transformations. And we're going to point out some key features to you of these log functions. And we'll deal with the transformations in a separate screencast to try to make this a little shorter. So here we go. So if you understand what a logarithm is, a log function would be any function that has this form: y equals log base b of x. The b could be any positive number other than 1. So kind of like exponential functions, there isn't just one basic function. You can have exponential functions with a base of 2, 4, 1/2. The same thing is true with log functions. You could have a log function with a base of 2, a base of 4, a base of 1/2. A couple of things to remind you of here, things that we explained last week. Remember, if we write a log without indicating the base, so for example, if I were to write an equation like this, that's what we call the common log. So we didn't put a little number down here, and that means you're supposed to know that the number is 10. So in other words, that function is exactly the same as this function because the base is 10, and that's what we call the common logarithm. Another notation is sometimes we might use the letter ln instead of log, and you are supposed to know that that's the natural logarithm, and now that means the base is e. E is that irrational number that we introduced to you when we talked about compound interest. It's approximately 2.7, but it's an irrational number like pi. It never terminates and it never repeats. So log function is any function that has an equation of one of these forms. Okay, so let's take a look at 3 different log functions. You can see at the top here we have log of base 2, base 4, and base 1/2. This is a good opportunity to maybe practice stuff you learned last week, which is how to evaluate a logarithm without a calculator. All the values on these tables you see here, you should be able to do without using a calculator. So I'm going to suggest you pause the screencast here for a minute, see if you can fill in these tables yourself, and then come back here and check your answers. So if you filled out the table, I will do the same here, and we'll just start on the left. So let's start with the easier ones first. If x was 1, we would be doing log base 2 of 1. In other words, we're asking you 2 to what power is 1? Well, 2 to the 0 power is 1. And then if we go down in the table, now we're asking you log base 2 of 2. So in other words, we're saying 2 to what power equals 2? Well, 2 to the first power equals 2. And hopefully you're getting the idea here. So 2 squared is equal to 4, and 2 cubed is equal to 8. The fractions are a little trickier. When x is 1/2, we're asking 2 to what power equals 1/2? That would be a negative exponent. 2 to the negative 1 power is 1/2. And similarly, 2 to the negative 2 power would be 1/4. So anyway, like I said, hopefully you remember what a logarithm is, and hopefully you were somewhat successful filling in the rest of these tables. One thing to point out here is that you might notice that every one of these tables has this same point, 1 comma 0. So that's something that we will discuss again once we actually look at some of these graphs here. So there are the tables for these three log functions, and now we'll actually go look at their graphs one at a time. Okay, so here is the graph for the first function, y equals log base 2 of x. I'm also showing you the exponential function y equals 2 to the x because we just want to remind you that these functions are inverses. That's how we first defined a logarithm, was by reflecting the exponential function. So just to reinforce that fact, notice that on the exponential function, if I take a point like, say, this one, which has the coordinate 2 comma 4, if I take that point and I switch the x and the y, I get a point on the red graph, 4 comma 2. And that's true for any point on the black graph and the red graph. Pick any point on one graph, switch the x and the y, and you should get a point on the red graph. That being said, there's one other thing I want to point out here that you might notice. So notice the black graph. Notice how this asymptote is shown going over here. Now remember, the point here, like if I were to draw a dot right here, that is the point where x is -8 and your y value is 2 to the -8th power. That is a really small fraction. 2 to the -8th is 1 over 2 to the 8th, and I have no idea what 2 to the 8th power is, but it's a really big number. The thing that I wanted to point out to you is notice that it doesn't look like on the red graph. How come we don't have a point that has -8 for a y coordinate? Well, it's because the x coordinate is so incredibly small. Whatever this number was, which was a really small fraction, that's what your x coordinate is over here. And the problem is it's just a limitation of the graphics. The software that generates these graphs, and this is true on a graphing calculator too, it just can't draw a line that's that skinny. So you need to understand that this asymptote does keep going down because you should have the reflection of that asymptote, right? So just something to be aware of when you look at graphs of logarithms, if they've been generated by a computer or by a graphing calculator. Sometimes it's going to look like the graph stops. Looks like the graph stopped right here, but it doesn't really stop. You have a vertical asymptote, and so that graph keeps going. Now, here's the graph of log base 4 of x, and again, you might want to confirm that the points on the blue graph match the table that we showed you a little while back. But notice that this graph, this blue graph, is not symmetrical across the diagonal line y equals x compared to the black graph. Again, if I pick a point on the black graph, like 2 comma 4, that point, if you switch the x and the y, that would be 4 comma 2, which would be right here, and that point is not on the blue graph. So this logarithm is not the inverse of the exponential, and that's because of something we wanted to point out that maybe you already realized. So exponentials and logarithms are inverses, but only if they have the same base. Log base 2 is the inverse of the exponential function with a base of 2, but log base 4 is not the inverse of the exponential with a base of 2. Because one has a base of 2 and the other has a base of 4. You have to have the same base if you want to be inverses. So here's the graph again of log base 4, and this time I'm showing you the exponential function with a base of 4. And now you can see the symmetry that we were looking for. The exponential curve has the point 1 comma 4, and the logarithm indeed has the point 4 comma 1. And because both of these are base 4, that's why they're inverses, and that's why you have the correct symmetry on these graphs. So finishing up, here's the third log function that we graphed, which was log base 1/2. As we just explained, it's going to be the inverse of the exponential function with the base of 1/2. So there's the exponential, there's the logarithm. You can see that these two graphs are indeed reflections across the line y equals x. So going back to exponential functions for just a second, here are the three exponential functions that we were looking at a few minutes ago. 2 to the x, 4 to the x, and 1/2 to the x. Some of the things that you should have learned when we studied exponentials is if you don't do any transformations, every one of these exponential functions passes through the point 0, 1, and that's what I would refer to as the starting point. So every exponential function, regardless of the base, passes through that same starting point. And the other important thing to point out here was that notice how the value of the base changes the behavior of the graph. Specifically, when you have a base bigger than 1, the graph is increasing. So the blue graph and the red graph both have bases bigger than 1, and both of those graphs increase as you move from left to right. But if you have a base less than 1, such as the green graph, then the graph doesn't increase, it decreases when you move left to right. The other thing to keep in mind is you cannot have a negative base. So when we say a base less than 1, that doesn't include negative numbers. We're talking about fractions like 1/2, 1/3, 1/4, and such. Well, since we've already established logarithms are reflections of exponentials, I hope it's not too much of a surprise that when you talk about log functions, if you reflect all those exponential curves, you get this picture here, and you can start to see we have similar things going on here. Specifically, every graph passes through this same point, which once again we will call the starting point. And it doesn't have the exact same coordinates, and that's because we switched the x and the y. So exponentials go through the point 0, 1, but logarithms go through the point 1, 0, and that's our starting point. And then again, you also have the same situation here where the different bases affect the shape of the curve. Notice that the logarithms that have bases bigger than 1 are increasing. In other words, when you go from the left to the right, the blue graph and the red graph get bigger and bigger y values. But the green graph, because it has a base less than 1, it is decreasing. So from the starting point, if you move from left to right, your y values are getting lower, not bigger. And that's a decreasing graph. So returning again to exponential functions, we already noted that basic exponential functions have a lot of things in common, such as the starting point. Here's a list of things that we taught you in Unit 8 about exponential functions. And again, we would remind you that logarithms are inverses of exponentials. And one way to understand inverses is that they swap the x and the y. So if you would take all of these facts that I circled, and everywhere you see an x, just turn that into a y. And similarly, everywhere you see a y, turn that into an x, because that's what inverses do. They swap x and y. Don't forget, domain is just another word for x, and range is just another word for y. So if you would take this list of facts and switch the x's and the y's, you would then come up with common features of log functions. Okay, so here are your list of common features of basic log functions. As we explained, all we've done is taken the common features of exponential functions and swapped all the x's and the y's. So everything you see here in red is where we changed what the statement used to say for an exponential function. Exponential functions have a domain that is always all real numbers, but we changed the word domain into range because that's a way of swapping x and y. We already noted that all basic log functions pass through the same starting point, which again is 1, 0, and that's why all log functions usually have an x-intercept of 1, because that's the starting point. So I hope these common features make sense when you think of it as they're just the features of exponential functions that have been swapped, had the x and the y swapped. The only other thing to point out here is notice, just like with exponential functions, notice where we're saying usually. And that's because I hope you know what's coming next. Pretty soon we're going to start talking about transformations. And if we start to apply transformations to these graphs, then we can change some of these features. So the domain is usually x is greater than 0, but if I apply a transformation, I can change it to something else. And the x-intercept is usually 1, but again, if I apply transformations, I could change it to something else. So hopefully you're getting the idea, and we'll talk about transformations in a separate screencast. So that wraps up basic features of log functions. Hopefully you have some sense of how to graph a log function. We definitely will be talking more about graphing log functions when we get into transformations, which is the next thing we're going to be talking about. Hopefully you have an understanding of what the domain, range, x and y intercept equation of the asymptote are for a log function. And the only thing left to do is to check your understanding. So kind of like we did with exponential functions, we have an assessment that we want you to try in its learning. It's called features of log functions. And just like with exponential functions, we've set this up so that you can do it an unlimited number of times. And we want you to keep doing this assessment until you get all the right answers. So a perfect score on that assessment is 8. And if you would try the assessment to test your understanding of basic features of log functions, make sure you keep trying the assessment until you get an 8 before you move on to the next screencast and before you start trying to do transformations of log functions. So good luck on the assessment, and we will talk to you in the next screencast where we address transformations.